Hi guys, here we are with lesson 2.1 on forces and Newton's first law. So what we're moving on to is a unit called dynamics. Dynamics is why things move, whereas kinematics, what we studied before, was how they move. So for example, how far can something be kicked, or how fast was the car going? Those are questions in kinematics. Why was the car going that fast, and why did the car slow down? Those are things that we'll discover in dynamics. So forces are what's at play in this entire unit on dynamics. They're why things accelerate, speed up, and slow down. The four groups of forces that we know, the fundamental forces of nature, are gravity, electromagnetism, weak nuclear forces, and strong nuclear. We're going to study gravity in Physics 20, and we leave some of these other forces for later physics courses. So gravity is an attractive force that governs the shape of the universe. All bodies have gravity exerted upon them in the universe. Depending on the mass and how far apart the bodies are, gravity will be different. Gravity acts over very long distances, and it acts through gravity fields. Now, these other forces you can read up on if you wish, but we don't need to cover that. So, as we learn more in science, the ideas will change through the scientific method. The things discussed here were developed in the early 20th century up until the 1970s. They belong to the school of thought called Standard Model of Physics. The discovery of quarks and other subatomic particles has increased our understanding, and some things have changed. But the old stuff is still very useful to us and still very true. For example, in 1687, at 23 years old, Sir Isaac Newton published the most important math and physics book of all time, the Principia Mathematica. It outlined three laws that governed all motion in the universe. We're going to study these laws in this unit. Even though these ideas are over 300 years old, they still hold up as a good basis for our study of dynamics. Newton's first law is what we'll look at today. It's also known as the law of inertia. So you might have heard this before as object at rest stays at rest, object in motion stays in motion. So this is an object continuing in a state of rest or state of motion at a constant speed along a straight path unless acted on by a net force. So this simply means that whatever an object is doing in terms of moving or not moving, it wants to maintain that motion unless a net force is acting on it. A net force is when you add up all the forces that are acting and what direction they're acting in, what vector would you be left with? So if we have an object at rest, we draw what's called a free body diagram. So this dot in the middle represents the object. So for example, me sitting here right now, not moving. There's a force acting on me in one way, there's a force acting on the other way, but if these forces are equal and in opposite directions, I don't move. Another example of that in the vertical would be the ceiling fan hanging from the ceiling. Gravity is acting on the ceiling fan, the bolts are acting on the ceiling fan in opposite directions, so the net force that that ceiling fan has is zero. If the net force is zero, it's going to stay exactly where it is. Here's some examples from the textbook. An object continuing in a straight path with constant speed. So imagine kicking a soccer ball. When kicked, you apply a force to the soccer ball, and that force allows the ball to accelerate in the direction that the force was applied. A while later, no force is applied anymore, but the ball is still moving. It's still moving with a constant velocity in a straight line. No force is needed to maintain this constant velocity. Force is only needed to accelerate the object. It'll only stop when a force is applied to it. And we know that when we kick a soccer ball, it does eventually stop. And that's because there are forces acting upon it, such as air resistance and friction. Some terms to get straight. First of all, inertia. Newton's first law is also known as the law of inertia. This is the natural tendency of an object to stay at rest or an object to stay moving that's already moving. Inertia is related to mass. The more mass an object has, the more inertia. It's harder to slow down a really heavy bowling ball than it would be to slow down a really light bouncy ball, for example. Now, mass and weight are often used incorrectly in media. Mass is the amount of space that an object takes up. So this is not the same as your weight. Your weight is the force of gravity acting upon an object. This varies planet to planet, and your mass is the same on every planet. So if I went to the moon, my mass would be exactly the same as it is on Earth. The amount of space that I take up on the moon is the same amount of space that I take up on Earth. However, my weight is the force of gravity acting upon my mass. So if the gravity of the moon is smaller than it is on Earth, I weigh less on the moon, but take up the same amount of space, so have the same mass. Now, the old tablecloth trick is a really good example of the law of inertia. So the items on the table want to stay at rest because they're already at rest. So if they are acted upon by a force, that's when you'll see them move. Okay, there's a small force of friction between the items on the table and the tablecloth, but this is a really smooth and shiny tablecloth that reduces friction just from what it's made out of. So if we move the tablecloth very quickly, the items on the table want to stay at rest. So if you do this fast enough, you should see that the items on the table stay just about exactly where they were. Now, what would happen if that force of friction wasn't reduced by a shiny, smooth tablecloth and moving it really quickly? Well, what you would see is that the friction acting on those items on the table would win out, and those items would be essentially ripped right off the table. There was a video here that won't work in this PDF, but it showed exactly that. All of the items on the table being pulled off because friction was winning. So here's a couple questions about inertia. Old cars were made of steel and then they barely dented when they were in an accident, but today we make cars with crumple zones. So they're made of materials that crumple easily. Why do we do that nowadays, and what are the safety benefits of this change? I'm attaching a video that explains the physics of car crashes, and it's a really nice illustration of what happens. When you have a crumple zone in a car, what it's essentially doing is absorbing the energy of the car crash. When you're sitting in a car, you're an object at motion, and you want to stay at motion unless acted upon by a force. In these old steel cars, the force that would act upon you to stop you is the steering wheel and the windshield. Those would stop you in a car crash. Nowadays, when we have crumple zones and airbags and seat belts and all of these other forces acting upon a person to slow them down in a car crash, that's making it much safer for us to be in a vehicle. Silly putty breaks when pulled apart quickly but stretches when you pull it slowly. Use Newton's first law to explain why. So silly putty, if you're just holding it in your hands, is an object at rest, and by Newton's first law, the law of inertia, it wants to stay at rest. If you pull it apart extremely quickly, you're applying a force, and what's going to happen is the silly putty wants to stay at rest is going to break. It's not going to absorb the force. It's going to break apart. If you pull slowly, then the silly putty that's moving slowly will stay in motion and continue to move with that small force that you're putting upon it. Here's the assignment for this week. There's some questions in the textbook, 2 to 8 on 136 to answer, and a reading of 126 to 142. It explains Newton's first law in different words than I've used today. What you want to do for this week is 1 hour of work. So including this video and all of this reading and textbook work, you want to put in 1 hour. If you don't finish it all, that's okay. We're just trying to get back into it and scratch the surface. Hopefully that was clear enough, but if you need more help with this, please don't hesitate to reach out to me.